starts analyzing polygons, and in particular talking about quadrilaterals eventually, and even more particular talking about parallelograms. And what happens is that there's a lot of properties that we need to learn and try to keep straight. Okay, and I'll try to give you the best way of doing that, and it's by building relationships, it's by learning the actual math instead of trying to memorize things. What we end up realizing is if we talk about a square all by itself, we'll be able to decipher all the features and properties and relationships that the sides and angles of the square and diagonals and all those kind of things have. And then we'll do the same thing with a rectangle. And we'll do the same thing with a rhombus. And we'll see that some of those relationships are shared by both or all three shapes. Some relationships are not. Some relationships are, there's one or two relationships that we can use every single time to look at a shape and classify it as one of those three things. But what happens is by themselves, the shapes and properties are easy to work with. When we then get on a test and all of these shapes and all of these properties are intermingled, we struggle. Okay, and so I just want to make sure that we have that understanding that if we know that it's going to be difficult when they get merged together, maybe we can approach these with a different mindset that allow us to really understand them on an individual basis. And the better we understand them on an individual basis, then the easier it'll be when they do get merged together. Okay. Today is just introducing what polygons are and some key theorems about the angles in a polygon. Okay. So the first thing is to talk about the prefix poly. Poly just means many, right? You guys talk about poly things in terms that incorporate the word poly in history, right? Polytheistic people that believe in many gods, right? Okay. So poly means many. Okay. If you talk about polynomials, okay, last year, nomial was term, poly means many, so many terms. Okay. So polygon, poly again meaning many. Gon is Greek for angle. Okay. Think about, trigonometry. There's a G-O-N in there, right? Okay. Tri meaning three, gon meaning angle, metry meaning measurement. Okay. So polygon, gon referring to an angle. So many angles. Here are a few characteristics. Each segment intersects exactly two other segments. Okay. So there's no, and basically what we say is that, and that happens at endpoints. So there's no overlap of segments or anything like that when we're making our polygons. We'll talk about this when we see some direct images. So each segment intersects exactly two other segments. No curves. Okay, so a circle is not a polygon. A semicircle is not a polygon. Anything that is curved is non-polygonal. All segments are coplanar. Okay, so all have to exist in the same plane. We'll see some examples of things that are not polygons based on that planar issue. And the figures must be closed. Okay. Mathematically speaking, closed covers a lot of different topics in mathematics. Basically, in this situation, all it means is that if we were to fill our object with water, there's no way of water leaking out. If we were to put an animal inside, let it be like a pen, and put an animal in here, if my cursor is an animal, it can't get out, right? It's closed. If we look at this one over here on the right, down here, is that one closed? No, that cursor can get out, right? Does that kind of make sense? That's what we mean closed by in this this situation. These are all polygons over here, okay, on the left-hand side, because they're all comprised or made of segments. Each segment intersects exactly two other segments. They're closed. There's no curves. And every segment is in the same plane. This shape is a polygon, right? It's closed. Each segment intersects exactly two other segments, and it does at endpoints. So there's no, like I said earlier, there's no overlap. We usually don't draw that line over and this line over. They both terminate there at C. There's no curves, it's closed. That meets all the conditions of being a polygon. Take this point, raise it. No longer a polygon. Okay? And actually, let's be more dramatic, or maybe easier to see if I raise maybe one of these points. Okay, it's still closed, still made up of segments intersecting exactly two other segments, no curves, okay? But all of these segments are not coplanar, okay? These three are in this gray plane, and then these two here that are sticking up are in that plane, okay? So that is not a polygon. Is that okay with everybody? Okay. These are not polygons. You know that first one, my cursor's in, has a curve to it, right? Okay. The next one, when we have polygons, we need to have an interior. Okay, that's what we mean by it being closed, is that there needs to be an interior. That Y shape does not have an interior. It's made of segments. Every segment intersects exactly two other segments. And when we say that, we should probably, when we say we intersect two other segments, we should say that this segment, like where my cursor is, should intersect two other segments at both of its endpoints. So let's look at this one over here on an actual polygon. Would you guys agree? Come on. There you go. That segment right there intersects exactly two other segments at the red segment's endpoints. That doesn't happen in that Y shape on the right hand side. Okay, so that's why that's not a polygon. The one on the bottom left here is not closed, so that's not a polygon. In this one here, how many segments does that segment there intersect? 3. Okay, intersects this one right there, intersects that one right there, and it also intersects this one here in the middle, okay? So it kind of folds over on itself, right? So when that happens, you do not have a polygon. Is that cool? Okay, now every single polygon is comprised of triangles. Okay, so that's why we spent so much time so far talking about triangles. And what we learn about these polygons is going to be based on what we know about triangles. Now, one of the things we like to do is kind of differentiate or classify polygons. Okay, so we've got this overarching understanding of what a polygon is now. Now we're going to kind of group different types of polygons. First type is called a convex polygon. Okay, and this is somewhat of a I think strenuous, confusing, sometimes definition. But remember, our purpose of definitions is so that nothing accidentally gets misclassified. And this definition does exactly what we need it to do so that nothing gets classified as being convex when it really isn't, or something that should be classified as being convex is not classified. Okay? This says a convex polygon is a polygon such that no line containing a side of the polygon contains a point in the interior of the polygon. Okay? And basically what that means is that you're going to take your polygon and you're going to extend all the sides of it. Okay? I like to do it one side at a time. And make sure that none of those sides actually pass through the interior of your polygon. So, give you an example of this. Okay, so I've got a 5-sided polygon here. How many, what do we call a 5-sided polygon? Okay, so this is a pentagon. All right, so what this says is that it says no line containing a side. And that phrase means you need to check this 5 times. You need to check it for every single side of your polygon. So what we're gonna do, I'm gonna start with this red side. And basically what I do is I extend that red side to create the line that the segment came from. Does that make sense? And I ask myself, okay, does that line that I just made, does that go through the inside or the interior of my polygon? And it does not. It follows the segment. Does that make sense? Okay. So far, this thing would be classified as convex. But we've got to check all 4 other sides. So now I'm going to go from A to E and check that blue side. And none of those points on that black line pass through the inside, right? So still convex. Same thing there. Still convex. Still convex. And the last one we have to check would be that one. So none of those 5 lines pass through the interior of our polygon, right? So this would be considered a convex polygon. Okay. Does that make sense? Now, if it's not convex, okay, what would that be? So the next definition, I think, is a terrible one, the way it's written. A polygon that is not convex is one that we call concave. And that's the definition. Concave polygon is one that is not convex. Well, one that is not convex would mean that we have to negate the definition of a convex polygon. So now, what we'd be looking for is a concave polygon is going to be one in which that line that we extended for each side goes through the interior. And you only need one line to do that. And if you have a concave polygon, there will be at least 2 lines that do it. Okay, there'll be at least 2 lines that pass through the interior. So we got 2 different types of polygons right now, convex and concave.
You said concave is like at least 2 lines that go in the center?
Yeah, so if we look at this one here, so do something like this. So I'm going to check these lines, and I'm going to check them in a manner of going from the blue one to the blue one. There. Okay, that passes, right? Okay, so checking the blue one, this is still convex. Check the purple one, still convex. Check that one, still convex. Now if I check this one, does this portion right here, does that pass through the interior? Okay, so that is enough to violate the convex polygon definition. So this becomes the default itself then to concave. And the only way that that point B can actually be created there is if there were another line that is going to violate the convex definition. So that other line would be that one there. So you do see 2 lines then that pass through the interior. Does that make sense?
So there will never be just one line?
There'll never be just one, correct. There could be, we could do something like this. So like there would be 4. Does that kind of make sense? Your polygons can get pretty nasty looking, pretty complex, but a lot of times we don't necessarily like these types of polygons, concave polygons, we don't deal a whole lot with at this level. Basically what's going on here and what we're going to do is, and what we have kind of already been doing a little bit, is the fact that we've got polygons, which is an overarching group, okay? Then we're going to have these convex polygons as a subgroup, and we have concave as another subgroup. Now, of these convex polygons, there are some that we've already dealt with, okay? I'm gonna right now just type in the word regular here. And then over here, I'll say irregular. Regular, all that means to us is that we've got equilateral and equiangular occurring at the same time. But with regular polygons, we've had triangles. Okay, now we've had multiple classifications of triangles, isosceles, or sorry, equilateral and equiangular. In this irregular polygon list, we've talked about some triangles. Spell triangles, right? Okay. But over here, what we're going to talk about next is maybe some quadrilaterals. And when we talk about quadrilaterals, we like to talk about parallelograms. Okay, and then when we talk about parallelograms, those will branch off to other things as well. But essentially, kind of a flow chart of shapes. And the irregular polygons is really going to be, you know, more triangles. There'll be more quadrilaterals over there. But that's kind of the, and I apologize. I should have put, no, that's fine. There'll be a branch of quadrilaterals here that might be regular, irregular. There might be, or not regular. They're irregular, but there'll be parallelograms as well. We're trying to classify things. Does that make sense? Okay. The way I remember these two terms on which and how to classify a shape, a polygon as being concave or convex. You guys ever, in science, you guys talk about like a spoon? You look at the reflection in a spoon and your reflection's upside down. Has you ever looked at that, talk about that in science? Look at the other side of the spoon and it's different. You've never done that? It's because of the concavity of that spoon. Okay, a spoon is got a little bit of a bowl shape to it, right? Okay, so basically what happens is you start with a flat piece of metal, they stamp it, okay, and it starts to create the way light waves travel. It creates some refraction with the light waves that flip that image, okay? But the idea is that the spoon is bowed in, right? Or it's pushed in, it's bowled out. It's caved in. Does that make sense? Would you guys agree that this side, so if I start with this here, that's convex, right? If I push on point E, did I cave point E in? And then that shape would be concave. Does that make sense? Okay. So that's how I remember what concave and convex, which one's which. And it's hard. Like I've been doing this for like 20 years now. And I always, whenever I talk about concave and convex and I'm talking about it, I'm always thinking in my head before I say convex or concave, I'm trying to think, okay, which one's pushed in? Okay, concave is pushed in, so that tells me which word I need to be using. Okay. Polygons are named based on the number of sides. Number of sides is equivalent to number of angles. So we go back to the definition of polygon, meaning many angles. Some textbooks will say that your name of your polygon is based on the number of sides you have. Some say it's based on the number of angles. It doesn't matter because they're identical. Okay. Polygons. Let's look at a list of the polygons here real quick. Just give you a set of names here. Let's do a quick Google search. All right, so when we talk about so here are our units, our ones place. So obviously polygon, we can only have, the first polygon we can create is a triangle, okay? We don't usually call it a trigon, call it a triangle, okay? A quadrilateral, we usually don't call it a tetragon. We could, you do see that sometimes in advanced textbooks, but we usually call it a quadrilateral, okay? But after that, we start using the gon, was that a suffix at the end? Okay, so pentagon for 5, hexagon for 6, heptagon for 7. Sometimes you might see septagon as well here. Octagon, 9 is a neagon. Okay, you've probably never heard that one before, right? You've heard octagon, correct? Okay, you've probably heard decagon. Deca stands for 10, right? Hendeca is 11. You guys have heard of dodecagons. That's 12. That's usually a common one to use. But these other ones kind of start to, for lack of a better word, suck. So triskidecagon, tetrakidecagon. So this chi, if we look at that, is like sticking together. It's like our teens. Does that make sense? Okay, so when I say 16, I'm sticking together a 1 and a 6, right? So when they say pentakideca, penta referring to 5, deca referring to tens, and that chi sticking them together, so 15. Does that make sense? So pentakideca, we got hexakideca, heptakideca, all that kind of stuff. We get to our 20s, we get an icosagon, 20-sided. Icasi, I can't even say half these. But you start to see that they get to be kind of a pain in the butt, right? So when we're talking about these, I want you to know 3 through 8, 10 and 12. Okay, I'm not a big, don't worry about hendecagon or a neagon. But anything else, and even those from time to time, they will abbreviate using, like this. If I say like 8gon, that's another word for octagon. Does that make sense? Or another notation for it. If I say 4gon, that's quadrilateral. Okay? Usually, they'll use the word octagon. They'll use the word quadrilateral. They will not use the word triskidecagon. They'll say 13gon. Does that make sense? Okay, so that's the way that we do that notation. All right, so polygons can be equilateral. Polygons can be equilateral, and all that means is that all sides are congruent. And I drew this one intentionally like this to demonstrate that just because the sides are the same does not mean the angles are the same. Would you guys agree those angles on the left and the right? Those are acute angles and all the other ones are obtuse? So all 6 angles up there are not the same. So equilateral for a polygon does not imply equiangular. Okay? It does for some polygons, but in general, all of them, it does not apply. Equilateral, all sides are the same. So then, equiangular would be something like this, where all the angles are the same. And I drew this one intentionally because now you can see that the top and the bottom are probably not the same length as the sides, right? Or the left and the right sides. So, in this case, equiangular does not imply equilateral. Just because something is equiangular does not mean it's equilateral, and vice versa. The reason I talk about that is because so far, we have said that would be true. Okay, if we go back to chapters 3 and 4, we have said that every single time you had an equilateral triangle, it was also what? Equiangular. That is one special polygon that exist for that equiangular implies equilateral or equilateral implies equiangular. In general, all polygons do not have that relationship. Okay? Only special ones do. Okay? Those special ones are referred to as regular polygons. Okay? So when we talked about an equilateral triangle in chapters 3 and 4, what we're really talking about is a regular polygon because it had equal sides and it had equal angles. Okay? A stop sign is a regular octagon. All the sides are the same length, all the angles are the same measurement. Okay? It's a hexagon up there. Okay? It's a regular hexagon. As you guys are writing that down, I'll draw some other things up here in a moment that we can talk about. 1, 2, 3, 4, 5, 6, 7, 8. All right, both shapes up there. Both of those are octagons. If I say the word octagon, which one do you think of though? You think of the one on the bottom right, correct? Okay. That one on the top left, 8-sided polygon. It's convex or concave? It's concave. Okay. But it's 8 sides. Okay. It is an octagon. It's just not the one that we are accustomed to. This would be irregular because the angles are all different, and the sides are all different. Okay? The one on the bottom right would be regular. Okay, if I look at the sides on all of this, on all of these over here on the bottom right, two, two, two. Okay, I think you get the point there, they're all 2. And if I look at the angles, they're all 135. Okay, so that is regular. This one, all the angles are different. Some of them are reflex angles, meaning that they're bigger than 180 degrees. Okay? However, they're both still classified as octagons. Just the one on the right, we can do a lot more work with than the one on the left. Okay? The one on the left is kind of chaotic and doesn't allow us to, like the generalizations that we can make about this one would not help us with, let's say, 3, 4, 5, 6, 7, 8. So that's an octagon too. Okay? But knowing something about this octagon up here, that blue one, tells me really not a whole lot of anything about that red one. Does that make sense? However, knowing something about this octagon here, this regular octagon, tells me a lot about that regular octagon. Does that make sense? Okay, so that's what we're going to be interested in. And what it really tells me is that those angles in that regular octagon are still 135 each. So regular means that we have both those characteristics. Okay. Now this is going to help us get, this next definition is going to help us get into being able to really recognize the number one feature about polygons. Okay, so we need to know what a diagonal is. A diagonal, okay, you guys have used this word in and out of mathematics, okay, for probably multiple years. But the mathematical definition is that it is a segment joining 2 non-consecutive vertices of a polygon. Okay, we use the word diagonal sometimes in like everyday language. We don't maybe interpret it the exact same way as this is. Okay, but a diagonal is a segment joining 2 non-consecutive vertices of a polygon. So, what's non-consecutive mean? Right, not not one after another. So if I say like Monday, Tuesday, Wednesday, those are consecutive days, right? Monday, Wednesday, Saturday, those are non-consecutive, correct? Okay, because they're not one after another. So, let's see here real quick. If I look at point A, and I ask you to find me a vertex that is non-consecutive to A, non-consecutive to A, what would be one of those vertices? D would work, okay? So if I go A to D, that right there is a diagonal. Okay? What would be another option? C. Okay? And that would be a diagonal. All right? Now, I could have also started at C or any other vertex here. If I started at C, what would be non-consecutive to C? A and E, right? Now, as I do this, and let me see, I think I can, maybe, there we go. Control C, V. All right, I believe those are all the different kind of situations we could have by looking at different vertices to start with, right? Are those triangles that are created, are they different triangles? Could they look like they might be different triangles? Yeah, okay. But in each one of those situations, are there 3 triangles? Yes, okay. So each one of those, so if I asked you, if I gave you a blank pentagon in front of you and said, draw the diagonals, okay, or draw one set of diagonals, there could be a lot of different correct answers, right? All right. The one thing we don't want to do when I say draw the diagonals is to draw all of them from all vertices at once. So we don't want to do something like this because that gets pretty messy, right? Okay. So when we talk about the diagonals, and for the purposes of the class right now, we're looking at from one, just choosing one vertex, it doesn't matter which one, and drawing segments to non-consecutive vertices. All right, give me 1 second. All right, so when we have a polygon, so this has got, 6 sides? So it's a hexagon, right? And we can move these segments around. Should be able to. No, maybe not. We got a hexagon here. And if I draw the diagonals, we can see those diagonals right there, correct? From this vertex. If I draw those diagonals and then pull those things apart, how many triangles do I get? I get 4 triangles. How many degrees are there in this triangle right here? 180, right? How many are in this one? 180. How many in this one? 180, right? How many in that one? 180, okay? Now, if there's 180 times 4, correct? Okay, so that's 720 degrees. If I move those triangles back together, did any of those 720 degrees disappear when I do that? No, right? They're still there. Now, whatever this angle here was, that, you know, that's less than 90. That's less than 90, less than 90, less than 90. When we merge them together, that sum might be greater than 90. Does that make sense? Okay. So that angle right there is the summation of these 4 angles, okay, this angle right here is the summation of those 2, and so forth down here, down here. But if I've got 4 triangles of 180 degrees, then when I have a hexagon, there should be 4 triangles of 180 degrees, so 720 degrees here. If I were to ask this thing to find the angle measurements of this shape, let's see here. Find that shape. And then, I'm not sure where that went. There it is. So the angles of that shape. So if I take all these angles, I know it's hard to see. Let me zoom. If we were to take those 6 angle measurements and add them all together, you would get 720 degrees. Does that make sense, everybody? It's because of the 4 triangles that make up that hexagon. If I had a 1, 2, 3, 4, 5, 6, so it would be 7. So let's look at would you guys agree that's a diagonal? Diagonal, 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 right? How many triangles you got there? You got 5, okay? So let's do a little bit of this is called a proof by what we call induction. And induction means recognizing patterns. So everything we've done so far with proofs has been deduction, using previous facts. So right now I'm going to look at n equaling 3, and then how many triangles can I have? So if I've got 3 sides or 3 angles, that would be my image, right? I can only have 1 triangle. So that's fine. So now if I go n equals 4, so I have 4 sides, my polygon has 4 sides. How many triangles can I have there by connecting diagonals? There's 1 diagonal, right? So 2 triangles. Let's go, n is 5. 1, 2, 3, 4, 5. If I go from 1 vertex, make my diagonals, how many triangles do we get there? 3. We just did 6 and saw that we had 4 triangles, right? We just did 7 as well and saw that we would get 5 triangles. What is the relationship between the number of segments or number of angles and the number of triangles that you can get? Right. So if I start with n being the number of sides, if I remove 2 from it, that's how many triangles I'm going to get. Does that make sense? So n minus 2. So if n is the number of sides that your shape has, n minus 2 is then the number of triangles that you can make, or that comprise your polygon. If I then take that number, multiply it by 180 degrees, because each triangle has 180 degrees in it, that gives me the number of angle measurements in that type of polygon. Now this is only right now for convex polygons. Okay, so we're not talking about concave ones here, just talking about convex. This is the sum of the measure of the interior angles of a convex polygon with n sides is n minus 2 times 180. N minus 2 times 180. N minus 2 tells you how many triangles you're going to get. Multiply them then by the 180 degrees in each of those triangles, and you've got your measurements. Now, we're not going to, I'm not going to ask you this or require this of you, but, you know, if n is 3, you're going to have 180 degrees. That's a triangle. If n is 4, you get 360. If n is 5, you get 540. If n is 6, you get 720, okay? Those are the ones that we're going to come across the most. So eventually, they become like common knowledge, kind of like 180 being common knowledge right now for triangles. We've used it so much. Quadrilateral is 360 degrees. On the other two, pentagon, hexagon, 540, 720. Octagon, I think octagon is 1080. 6 times 180. Yeah, 1080. Does that kind of make sense to everybody? Now, the next one says, the next bullet says, if I have a regular plane, this has to be regular, which means it has to be equal angular, right? And equilateral. Okay? If I want to find one angle in a regular polygon, okay, let's go back to our octagon picture we had previously. Okay, we just said n there, so 8 sides, so n would be 6, right? So if I take 6 times 180, that should give me 1,080 degrees. If I take all these angles and add them up, I get 1,080 degrees. But what do we know about each one of these angles? If it's regular, they're equal. So how can I find one of them? But if I know they're all going to add up to 1080 without using a measuring device, if I know they're all going to add up to 1080, and they're all the same, I'm going to divide by 8. So I'm finding the average, right? So if I take 1080 divided by 8, it gives me 135, right? If I ask this to find the angles, do they all turn out to be 135? All right, so that is that. And you heard me say the average, and that's what we're doing here. We're taking how many we have, okay, and dividing by n. Okay, so the sum of our angles, n minus 2 times 180, that's the sum of all our angles, and then divide by how many angles you have, and that is an average. And it's saying 135 in that case. Okay, so that's finding one individual interior angle of a regular polygon. Questions so far? So, what's going to happen is that we go back to what we've already done in our work with triangles. If I gave you a triangle sum of the angle, said it was 180. All three angles ask for 180. And I gave you 2 of them. Could you find the third one? Yeah, you do subtraction, right? Okay. So now we have, what do we have here? Pentagon. Okay. Pentagon has 5 angles. How many of these angles do you know? 4. Okay. So can I take the total of a pentagon? So the total of a pentagon would be n minus 2 times 180. So that'd be 3 times 180, which is 540, right? So all 5 of these angles need to add up to 540. If I know 4 of them, minus 110, minus 90, minus 120, minus 150, will that then give me my measurement for angle Y? Okay. So what's that? 200, so 340, 220, so 70? 70 degrees for that angle right there. That kind of makes sense. Is that the same thing that we've done with triangles? Yeah, okay. But now each question is going to change because then we might do that for question 1. Question 2 might have a different total because question 2, instead of being 6-sided, might be, or 5-sided, might be 6-sided. And question 3 might be 8-sided. Question 4 might be 12-sided. Does that make sense? Okay. So you're always going to have to find a different total and then subtract away the parts that you do have. Now we could do that with just numerical values. We can do it with, I don't know if I have any example. We could do it with algebraic expressions here. Okay. One thing I want to look at real quick with you is an exterior angle. Let's go and we'll be done. We've talked about exterior angles for triangles before. And basically what we talked about with an exterior angle was that we are going to take from like vertex A, we're going to travel to the next vertex. And it doesn't matter which direction you go. But then once you hit the next vertex, just keep going. All right, and we get this exterior angle out here, right? Okay. Now that exterior angle is supplementary to this interior, correct? Okay. And then we're going to do the same thing for that vertex going to the next one in the same direction. And we'll do the same thing here. We'll do the same thing there. Same thing there. Same thing there. Same thing there. Is that okay with everybody? So we get these exterior angles. Now, I don't know how easy this will be to get these exterior angles to show up here. Yeah. Okay, so if I go through and add these angles up, okay, so I'm going to see if we can do this. Where'd my input bar go? All right, so it's kind of a pain in the butt because of the lettering here, but A, beta, gamma, epsilon, tau. All right. All right, so if I add all those up, anyone want to guess what they're going to add up to? 360. Okay. Now, no matter what we do, and I believe I've got a website here somewhere to show this.